Let's examine the motion of a charge in a uniform magnetic field. What we will learn is the guiding principle for the design of a cyclotron, which is a type of a particle accelerator. So let's consider a proton which is moving perpendicularly in a uniform magnetic field. So the magnetic field is shown here going into the plane of the board as marked by the X marks, and it is uniform throughout this region where the proton is moving. Initially, the proton is moving in this direction with the speed v. According to Lorenz's rule, the Lorentz force is given by v cross b times the charge, of course. And applying the cross product rule, you can see that the force due to the magnetic field is downwards as shown here by the red arrow. Since the velocity of the proton is perpendicular to the magnetic field, and since the force always due to the magnetic field is always perpendicular to the magnetic field, there is no work done on the proton. And since the velocity is perpendicular to the field, its motion will always stay perpendicular to the field in the plane of the board. And this motion will of course be a circular motion. So there is a centripetal acceleration, and that acceleration is v squared by r. We know that very well. And mass times the acceleration gives us the force, and this force has to equal the Lorentz force. The Lorentz force is just v cross b times the charge. That's E, V, and B. Therefore, this expression gives us a way to calculate what is the radius of the orbit. So one of the velocity terms cancels here, and the radius of the orbit is simply mass times the velocity divided by the charge times the magnetic field. So let's just make sure that this makes physical sense. So if the particle, the proton, was moving with a very large velocity, then of course depending on the intensity of the magnetic field doesn't have that much of a chance to bend the direction of motion of the proton. So its radius will be larger. That's what this equation suggests. If the particle had a larger mass, of course it has more inertia, and it will take up an orbit with a much larger radius. On the contrary, if the magnetic field is very large, the radius has to be smaller because the effect of the field is larger. So the magnetic field comes in the denominator. The time of one revolution in the circular orbit is easily calculated. It is simply the distance traveled in one orbit, which is 2 pi r, divided by the velocity. So the time of the orbit for one orbit is 2 pi r divided by the velocity, which, given the expression for the radius that we found in the previous slide, we see that it turns out to be 2 pi m e over b. So this is a remarkable result because it is independent of the radius of the orbit. What is involved here is purely the properties of the particle, the mass and the charge, and of course the magnetic field. And since we've decided to keep the magnetic field uniform over this entire region, no matter what the radius of the orbit is, the proton is going to take the same amount of time. So this is the building principle, or the principle behind the design of the cyclotron. So this picture here shows the physical construction of the cyclotron. It has two D-shaped objects, and they're metallic plates, two parallel plates with an angular space in between which the charge can move. And one is able to apply an oscillating voltage between the plates. There is also a gap in the straight part between the two straight parts of the Ds, and the voltage actually appears, the electric field due to the voltage actually appears between the two plates in the gap here. So if a proton starts off at the center, let's say it's moving in this direction, it's bent because of the magnetic field, and the time it takes to complete one circle is always the same. So it gets accelerated, and because it gets accelerated, it's going to take a larger radius because of the magnetic field is constant. And even though it may be traveling in a larger radius, the amount of time that it takes to complete half cycle is always the same. So it gets accelerated here, it's faster. When it comes over here, the time taken to get over here is the same. It gets accelerated again, and the time taken, however, to complete that circle is also the same. So what this enables us is to set this oscillator at the correct frequency, so that when the proton comes from there to there and is accelerated and travels this distance in that half the period, you switch the voltage from one direction to the other, the electric field from one direction to the other, so it gets accelerated again at the gap. So this periodic switching is what makes the proton spiral faster and faster, and eventually it comes out of the cyclotron at a very large velocity. Now, if the proton reaches such large velocities that it's in the relativistic regime, then of course the period changes, because the mass of the electron according to relativity is changing.